A new technique to identify dynamic model of a real time system will be discussed in today's lecture. The dynamic transfer function model can have a stable pole or an unstable pole. Let us see the relay autonomous closed loop system, where the system real time system is represented by the dynamics given as k e to the power minus theta s upon t 1 s plus minus 1. So, the denominator shows us that a pole in the right half or in the left half can be there for the dynamic model of the real time system. Then a relay is connected in this fashion, disconnecting the controller PID controller to induce limit cycle output. Then the limit cycle output or the sustained oscillatory output assumes this form, where this is the y t versus t, the output we get from the system corresponding to the input to the system which is generated by the relay. So, the input to the system is now u t versus t given as, this is our u t versus t, and we assume the relay amplitudes to have magnitudes of plus h and minus h. So, we shall make now 3 measurements on the sustained oscillatory output, unlike the previous lectures where we used to take 2 measurements only, and those are nothing but the peak amplitude given by A p, half period denoted by P u by 2, where P u stands for one period of output of the system. Now, we make additional measurement, and that is nothing but the slope of the output signal at the zero crossing, and slope will be designated by S. So, immediately after the zero crossing, we shall measure the slope of the sustained oscillatory output of the relay control system. So, the relay induces this type of typical signal, and we shall make 3 measurements, namely S, the slope of the output signal at the zero crossing, A p, the peak amplitude of the output signal, and half period of the output signal given by P u by 2. Consider, for analysis of the dynamic system now, closed loop system now, relay control system now, consider the first order plus dead time plant transfer function G s is equal to k e to the power minus theta s upon t 1 s plus minus 1, which is nothing but equal to y s upon u s, where y is the output and u is the input to the system. Then cross multiplication will result in t 1 s y s plus minus y s is equal to k e to the power minus theta s u s. Again, when the inverse Laplace transform is taken, the same expression is given by y dot t is equal to minus plus 1 upon t 1 y t plus k upon t 1 u t minus theta. Thus, we have got delayed input to the system u t minus theta. When the state variable x t is introduced, x t is equal to y t, then the dynamic equation in state space can be written in the form of x dot t is equal to minus plus 1 upon t 1 x t plus k upon t 1 u t minus theta. That is what we have obtained. Let us assume x dot t to be expressed in the standard state equation form of x dot t is equal to alpha x plus beta u t minus theta, where alpha is now minus plus 1 upon t 1 and beta is equal to k upon t 1. Why we are writing this in this standard state equation form? Because we know the solution of the standard state equation, which can be used further for analysis. Now, the initial slope of the output signal after a zero crossing, which is nothing but this one at the zero crossing. If we take the time t equal to 0 from this instant onwards, then the output at that instant will be y 0, whereas the first derivative of the output at that instant will be y dot 0, and we know that y t is equal to x t. Therefore, y dot 0 is equal to x dot 0 is equal to the slope of the signal as k h by t 1. How do we get this k h by t 1? From this equation number 1. Now, I can write the equation number 1. 1 can be written as x dot 0 is equal to alpha x 0 plus beta u t minus theta. We know that x 0 is equal to y 0 is 0, x 0 is equal to y 0 is equal to 0 at the zero crossing. Therefore, x dot 0 will be equal to beta u t minus theta, which is nothing but k upon t 1 u t minus theta. Now, u t minus theta will have two values, either plus h or minus h, depending on the time range. Now, u t minus theta is equal to h for us, because we know that the input to the system u t minus theta is equal to h for the time range 0 is less than equal to t is less than equal to theta. Therefore, x dot 0 will be equal to k h upon t 1. That is what is given in equation number 2. So, the slope of the output signal at the zero crossing is given as s is equal to k h upon t 1. What type of output and input signal we get? Let us consider half period of the output signal, where the output signal will be of this form. This is the time axis. So, time p u by 2, because we are considering the half period, and then the input to the system will be of the form where this is h and this one is minus h. Now, what is the output? Peak output. Peak output is nothing but y theta is equal to a p, the peak amplitude. And also we know that x 0 is equal to y 0 is equal to 0. So, the output at a zero crossing is equal to 0. This is the plot for u t minus theta. Keep in mind, this is not the plot for u t, this is the plot for the rectangular pulse we are getting. It's the plot for u t minus theta, delayed input to the system, whereas this is the plot for output, sustained oscillatory output of the system. Now, we know that the general solution of the standard state equation given in 1 can be written as x t is equal to e to the power alpha t minus t 0 x t 0 plus integration from t 0 to t e to the power alpha t minus tau beta u tau minus theta d tau. So, this is the standard solution for a state equation given in the form of x dot t is equal to alpha x t plus beta u t minus theta. So, when the state equation is of this form, we get a solution of the state equation of this form. Now, we shall use this standard solution to find analytical expressions for the output, sustained oscillatory output of the system till time t equal to p u by 2. We know that x 0 is equal to y 0 is equal to 0. Therefore, the expression for the present case can be written as x t is equal to integration from t 0 to t e to the power alpha t minus tau beta u tau minus theta d tau. But for the time range, time range 0 is less than equal to t is less than equal to theta, we know that the input u t minus theta is equal to u tau minus theta is equal to positive h. Then the x t can be written as x t is equal to e to the power alpha t, then integral t 0. Now, t 0 equal to 0, we start the analysis from time t equal to 0. Therefore, this will be 0 to t, then e to the power minus alpha tau d tau times beta h. This integral can further be simplified giving the expression x t as e to the power alpha t. I will take minus alpha inverse, then e to the power minus alpha tau with the limits 0 to t with beta h, which becomes now e to the power alpha t minus alpha inverse, or we can write this in the form of minus alpha whole inverse, then it becomes e to the power minus alpha t minus 1 beta h, which can ultimately be written in the form of alpha inverse e to the power alpha t minus 1 beta h. So, what we have got from the analysis, that the output of the signal can be expressed, the analytical expression for the output of this part of the output signal can be given by x t is equal to y t is equal to alpha inverse times e to the power alpha t minus 1 beta h. Now, solution of this. So, the solution of 1 has been found in this form. For the time range, for 0 is less than equal to t is less than equal to theta. What about when t is greater than equal to theta? Let us find the solution for that time range first. So, since x t is equal to alpha inverse e to the power alpha t minus 1 beta h, then x theta will definitely be equal to alpha inverse e to the power alpha theta minus 1 beta h. But for the time range, t is greater than equal to theta, we know that the input changes, u t minus theta is equal to u tau minus theta is equal to minus h. H, we have seen that the input, this is time t equal to theta. So, when t is greater than equal to theta, the input becomes minus h. Then the solution of the state equation y t is equal to x t will be e to the power t alpha t minus theta x theta plus theta to t e to the power alpha t minus tau beta u tau minus theta d tau. Why that is so? We need to substitute T0 equal to theta in the general solution for the state equation. Then we get this expression. Then substitution of x theta in the above results in alpha inverse e to the power alpha t minus e to the power alpha t minus theta beta h. This is what we get from the simplification of the first term and by substitution of x theta, where x theta is given as alpha inverse times e to the power alpha theta minus 1 times beta h. Then the second part, the integral part, can further be simplified, giving us e to the power alpha t minus alpha inverse e to the power minus alpha tau with the limits theta to t now, and we are left with minus beta h, because the input is minus h now. So, which further upon simplification gives us alpha inverse e to the power alpha t plus 1 minus 2 times e to the power alpha t minus theta beta h. So, this is what we get for the time range t is greater than equal to theta. Let us see whether this expression is valid or correct or not. The correctness of this expression can be found by the substitution of t equal to theta. So, when t equal to theta, what I get? T equal to theta will give me x theta is equal to alpha inverse e to the power alpha theta plus 1, then minus 2 e to the power 0 now times beta h. So, this is nothing but is equal to alpha inverse e to the power alpha theta minus 1 times bh, that we have obtained earlier. Therefore, the expression we have obtained for the time range t is greater than theta is correct. After ascertaining that, we will go to the analysis of the half period of the sustained oscillatory output, where we know that the output becomes 0 at time t equal to pu by 2. So, that can be given in the form of y pu by 2 is equal to y 0. Actually, since we get sustained oscillatory output, so y pu by 2 has to be equal to minus y 0. As we know, the output possesses half wave symmetricity. Therefore, y pu by 2 has to be minus y 0, or in general form I can write y t plus pu by 2 has to be minus y t, and since y t is equal to x t, which can further be given in the form of x t plus pu by 2 is equal to minus x t. So, the limit cycle condition or the output will have sustained oscillatory form, provided that condition is made. What is that condition? X t plus pu by 2 has to be minus x t, or I can write this by substitution of t h 0, x pu by 2 is equal to minus x 0. What is x 0? The x 0 is equal to y 0, which is nothing but 0, because we start our analysis from time t equal to 0, at which we have the output of the system 0. Therefore, this is equal to 0. So, when I substitute t is equal to pu by 2. So, when t is substituted by pu by 2, then x pu by 2 will be equal to e to the power alpha inverse e to the power alpha pu by 2 plus 1 minus 2 e to the power alpha pu by 2 minus theta beta h, and this has to be equal to 0, that we know from this condition. Then this expression now can be written in this form: 2 e to the power minus alpha theta minus e to the power minus alpha pu by 2 minus 1 is equal to 0. Why that is so? Because alpha is a constant and beta is a constant. Therefore, this expression is equated to 0. Again, if I multiply both sides of this expression by e to the power minus alpha pu by 2. So, multiplication of this factor to both sides of this equation will result in this. So, one can say this is the extended version of this one for each in analysis. So, this expression 3 meets the requirement on the limit cycle, condition for the limit cycle. So, this has to be satisfied, otherwise one cannot guarantee sustained oscillatory output from the system. Now, peak output of the system occurs at time t equal to theta. Now, that peak output, expression for the peak output can be given in the form of y theta is equal to x theta is equal to the peak amplitude given as alpha inverse e to the power alpha theta minus 1 beta h. What has been done here in this expression? The t has been substituted by theta. Then we get the expression for the peak amplitude, peak output of the sustained oscillatory signal. Now, we know that the constant alpha is equal to minus plus 1 upon T1 and beta is equal to k upon T1. So, substitution of alpha and beta in 4 results in an expression of the form AP is equal to minus plus T1 e to the power minus plus theta by T1 minus 1 k upon T1 h, which is equal to T1 is cancelled out. So, that way we are left with minus plus k h e to the power minus plus theta upon T1 minus 1. So, this is the expression for output of the first order plus time delay transfer function model. So, when we take minus sign and when we take plus sign, so for stable process models, we shall use the upper symbol and the upper one, and for unstable system, the system's dynamics will be or can be obtained using this expression where we shall choose the bottom sign. So, for an unstable first order plus date time model, we shall go for the lower symbols plus here and plus here, but for a stable first order plus date time transfer function model, we have to use the upper symbol minus here and minus here. Now, after obtaining this one, let me give this as the same equation number 4. Again, substitution of the same alpha and beta in equation number 3 will result in, what is equation number 3? We know that this is our equation number 3, 2 e to the power minus alpha theta minus e to the power minus 2 e to the power minus alpha theta minus e to the power minus alpha pu by 2 minus 1 is equal to 0. So, substitution of alpha here will result in 2 e to the power, this will be plus minus theta by T1. Because of this minus sign, the pair will get inverted and then we will get 2 e to the power plus minus e to the power, it will be 2 times e to the power plus minus theta upon T1 minus e to the power again plus minus pu by 2 T1 minus 1 is equal to 0. So, this is our equation number 3. But we know that the slope of the output signal, the slope of the output at the 0 crossing is S is equal to Kh upon T1, which is given the same equation number 2. Thus, we have got 3 important equations. Let me write down those 3 important equations. S is equal to Kh upon T1, then 2 e to the power plus minus theta upon T1 minus e to the power plus minus pu upon 2 T1 minus 1 is equal to 0, which is given the equation number 3, and the peak amplitude given as minus plus Kh e to the power minus plus theta upon T1 minus 1 is given as equation number 4. Then we have obtained 3 important expressions, and also we are making 3 measurements on the output signal. Thus, the 3 expressions can be solved simultaneously to estimate 3 unknowns k, theta and T1. From the simultaneous solution of those equations 2 to 4, the 3 unknowns of the transfer function model, we have got the transfer function model now k e to the power minus theta s upon T1 s plus minus 1. So, the 3 unknowns in the transfer function model k, theta and T1 can be estimated using the 3 expressions. Now, one needs to solve the 3 equations simultaneously, because they have the parameters in them, all the 3 parameters are found in all the 3 expressions, so to say. So, that way simultaneous solution of the 3 nonlinear or linear equations are required to estimate the 3 unknowns. Now, the estimated parameters are exact. You will find exact estimation provided there are no sensor measurement errors. That means, if the output is, let us take this case, if the output is not error free, rather we get some output of this form, then one may not be able to make measurement of the slope. So, the information, the slope information may be inaccurate. In that case, the estimation of k, theta and T1 may be erroneous. So, one must take care of this fact. In those situations, what happens? One can make use of alternate techniques. Wavelet based measurement and noise reduction technique can be made use to obtain clean signal from the noisy output signal. So, the noisy output signal can be filtered out of all the noise components, and then we can get some smooth output signal of this form. Now, this smooth output signal may enable us to make all the 3 important measurements accurately. What are those measurements? The initial slope S, peak amplitude A p, and the half period pu by 2. So, when the measurements are error free and when the output is clean or output is not subjected to measurement errors, or the output is not subjected to external errors, erroneous or not subjected to extraneous error signals, in that case it is possible to estimate the 3 unknowns using the three expressions we have found earlier. Those expressions are given by the equations 2, 3 and 4. Now, let us little bit extend this analysis. Let us introduce one more parameter. Let mu is equal to AP by KH. But we know that AP is equal to, the peak amplitude can be given in the form of minus plus KH e to the power minus plus theta upon T1 minus 1. Then the expression AP can be written as AP by KH is equal to minus plus e to the power minus plus theta upon T1 minus 1, or mu is equal to minus plus e to the power minus plus theta upon T1 minus 1. Likewise, then it is not difficult to write an expression of the form e to the power minus plus theta upon T1 is equal to 1. Then 1 will come here. So, that way 1 minus plus mu. Why that is? How that is obtained? If I multiply minus plus on the both sides, if I multiply minus plus, then this will go out, this will be out. So, that is how we are able to obtain an expression of this form ultimately, which taking the natural logarithm further gives us minus plus theta upon T1 is equal to ln of 1 minus plus mu, implies theta is equal to minus plus T1 times natural logarithm of 1 minus plus mu. So, this is an important expression for us. The theta can be obtained using this expression later on, or using mu, where mu is equal to AP by KH. Similarly, we can start analysis for the third equation. So, again third can be written as 2 e to the power plus minus theta upon T1 minus e to the power plus minus pu by 2 T1 minus 1 is equal to 0. This is the equation number 3. Now, what I will do? We know that e to the power plus minus theta by T1 can be obtained from here. Using this e to the power plus minus theta by T1, sorry, not this one, the upper one. Using this e to the power plus minus theta by T1 will be 1 upon 1 minus plus mu. So, I can substitute that, giving us 2 upon 1 minus plus mu minus e to the power plus minus pu by 2 T1 minus 1 is equal to 0. That implies e to the power plus minus pu by 2 T1 is equal to 2 upon 1 minus plus mu minus 1 is equal to 1 plus minus mu by 1 minus plus mu. Further, taking the natural logarithm of both sides, we can get plus minus pu by 2 T1 is equal to ln of 1 plus minus mu by 1 minus plus mu, giving us T1 is equal to plus minus pu by 2 divided by plus minus pu by 2 divided by ln 1 plus minus mu by 1 minus plus mu. So, this is another expression for the one of the unknown of the transfer function model. Earlier we have got an expression for one unknown of the transfer function model, theta. Further analysis will be done, and we know that mu is equal to AP by KH. we know that mu is equal to AP by KH. That we have taken the approximation. We started our analysis with the assumption that with the introduction of a new variable mu h AP upon KH. Then we know that the slope of the output signal can be given as K upon KH upon T1, which means KH is equal to S T1. So, substitution of this KH in this denominator gives us mu is equal to AP upon S T1. Further, we know that T1 is this much. Therefore, if I substitute the expression for T1 over here, I get AP upon S times plus minus pu by 2 ln 1 plus minus mu by 1 minus plus mu. So, that will give us your plus minus pu by 2 divided by ln 1 plus minus mu by 1 minus plus mu. So, which will be ultimately mu is equal to AP times ln 1 plus minus mu by ln 1 plus minus mu by 1 minus plus mu divided by S times plus minus pu by 2. So, this is an important expression for us, because if you look carefully, then you can see AP is measured, S is measured, then pu is also measured. So, from the output measurement on the output, we get information about AP, S and pu. Therefore, in this expression there is only one unknown, mu. Then this can be solved, this expression can easily be solved to find out the mu, and once mu value has been found out, then substitution of mu and making use the measurement pu, we can estimate T1. Further, making use of T1 and use of mu will give us theta. That is how all the unknown of the transfer function model can be estimated. So, let me summarize. So, the expression for T1 is given as plus minus pu by 2 divided by ln 1 plus minus mu by 1 minus plus mu. Theta is equal to minus plus T1 time natural logarithm of 1 minus plus mu, and the steady state gain K is equal to S T1 by H, because we know that the slope is given by S is equal to KH by T1, then your K is nothing but S T1 by H. That is how we get expression number 7. And also we have found in our last slide that mu is equal to AP times natural logarithm of 1 plus minus mu by 1 minus plus mu divided by S times plus minus pu by 2. So, mu can be calculated from the solution of the equation 4. We have got one nonlinear equation where there is only one unknown, and since AP, pu and S are measured or obtained from the sustained oscillatory output of the relay feedback test, in that case mu can be calculated, estimated using expression number 8. So, using this expression 8 or equation 8, mu can be estimated or can be calculated. Once mu is known, then we can find T1, because pu is measured and mu has been estimated. Next, after getting T1, we can get K, because H is known, T1 has been calculated and S is measured. Then also we can find theta using mu. Mu T1 can be used to estimate theta. Thus, all the transfer function model parameters of the first order stable or unstable transfer function model can be estimated using the three measurements, made on the output of the system. So, this gives us some freedom, unlike the earlier case where we had to obtain the steady state gain by some other technique or assumed to be known a priori. We need not make any assumption in this case. The new technique enables us to estimate the three transfer function models conveniently using equations 5, 6, 7 and 8. Now, we shall go to some simulation example to verify accuracy of identification. Let us see whether our technique is accurate or not. So, in this simulation study, an unstable system, an unstable first order plus date time system transfer function has been considered, where the time delay theta is equal to 0.4 second. Now, the time constant t 1 is equal to 1 second and the steady state gain k is also equal to 1. If I look at this transfer function model for unstable first order plus date time model, the three parameters those have been given are k is equal to 1, theta is equal to 0.4 and t 1 is equal to 1. Let us try to estimate back these values from the equations. Now, when a relay test is conducted on this plant, on this first order plus date time transfer function model, the sustained output is obtained and the waveform of the sustained oscillatory output is shown over here, where this is our output y t. Now, let me draw the x axis, and what is the blue lines? This is nothing but the input to the system, delayed input to the system. So, we have got the blue lines are nothing but the rectangular lines are nothing but plot for u t minus theta. Let me start my analysis from the first zero crossing over here. So, this time is t is equal to 0 and we see that at time t equal to theta, a peak amplitude or peak output occurs. Now, what is this? This would be the half period t equal to p u by 2. So, if I look at the plot, my peak amplitude is obtained here at time t equal to theta, which is nothing but a p equal to y theta is equal to x theta. Now, how much is that a p? The accurate value we will try to estimate. If I look at this plot, how much I get this for the time half period of the signal? Half period of the signal is almost of 1 second or so, and the time delay till t equal to theta will be also of magnitude 0.4 or so. So, we will make a measurement has been made using some software, or theoretically we have to make use of some software to accurately estimate the parameters a p, p u by 2 and the slope at the zero crossing. So, if I look at the plot over here, the slope is found to be 1. The slope is found to be 1. So, let us see what sort of measurements are obtained from this output signal. So, from the simulation with the relay testing, with the relay setting of plus minus 1, a peak amplitude of magnitude 0.4918 is obtained. Half period of the output signal is found to be of 1.077 and S is equal to 1. So, these were estimated using some software. Now, I shall make use of the expressions we had for estimation of transfer function model for this system. Now, we know that mu is equal to AP times ln 1 minus mu by 1 plus mu by S times minus pu by 2. Why I am writing in this form? As I had mentioned earlier, for unstable system we have to choose, pick up the bottom sign. So, mu will be equal to AP times ln 1 minus mu divided by 1 plus mu upon S times minus pu by 2. So, that I have written over here. So, as I know AP and S are already obtained from the measurement. So, this is equal to minus 0.4566 times ln of 1 minus mu by 1 plus mu. So, when this nonlinear equation mu is equal to minus 0.4566 times ln 1 minus mu by 1 plus mu is solved, the solution gives us mu is equal to 0.4918. So, one may has to employ a nonlinear equation solver, or intuition can be applied. Many techniques are there to find or solve one unknown from one nonlinear equation. So, employing that technique, the mu can be estimated and the mu is found to be of the magnitude 0.4918. Then the T1 using the formula becomes T1 is equal to minus pu by 2 divided by ln 1 minus mu by 1 plus mu is equal to 1. Further, theta is equal to, by formula it is T1 times ln 1 plus mu. So, substitution of mu and T1 over here gives us theta is equal to 0.4. Thus, we have found that if mu can be estimated accurately, in that case the T1 and theta can be estimated accurately. What was the transfer function model we had? We had Gs is equal to e to the power minus 0.4 s upon s minus 1. As I have already mentioned, theta is equal to 0.4, T1 equal to 1 and k is equal to 1. So, our calculation from here, the k is equal to, as you have seen the expression for k. So, k is equal to for our case S T1 by H, S T1 by H, and S is equal to 1, T1 has been estimated as 1, H is equal to 1. So, k is also equal to 1. Thus, the estimated values theta, T1 and k are found to be accurate, and thus the dynamics of the real time system, the unstable plus first order plus dead time system has been found as Gs is equal to 1 e to the power minus 0.4 s upon s minus 1. So, let me summarize all the parameters of a first order plus dead time transfer function model, whether the transfer function model is for stable or unstable first order plus dead time systems, does not matter. All the parameters of the transfer function model can be estimated using the expressions we have derived. So, three expressions can be made use of to estimate the three known unknowns of the first order plus dead time transfer function models. The general expressions we have obtained can be extended for lower order dynamic models. What I mean by lower order dynamic model? When Gs is equal to k e to the power minus theta s, or Gs is equal to k bar e to the power minus theta s upon s, those type of transfer function models or dynamic of real time systems can be obtained. Now, output waveform can be observed to decide about the transfer function model. So, whether we have to identify simpler model or first order plus dead time model, those informations can be obtained from the observation of the output waveform. Now, model parameters are estimated using the 3 measurements and using the 3 expressions we have derived. Some points to ponder. Is there any other method to identify the model parameters of a first order plus date time model or first order plus date time systems rather? Yes, there are many techniques. To name a few, one can estimate the time delay parameter from the first derivative of the sustained oscillatory output when there will be large change in the output or when there will be discontinuity in the output, then the time taken to that point from any zero crossing can be taken as the time delay associated with the dynamics of that system. Then the remaining 2 parameters k and T1 can be estimated using any 2 expressions we have derived earlier. So, there are other techniques also to identify the model parameters of first order plus date time systems or higher order systems in terms of first order plus date time transfer function models. The second point is any limitation of the identification technique. Certainly, the identification technique is subjected to mainly 2 limitations. One is the ratio between the date time to unstable time constant of the first order plus date time unstable systems. If this ratio is not large, then only a sustained oscillatory output can be obtained. That is one of the limitation of this identification technique. Secondly, sustained oscillatory output must be noise free, otherwise it will be very difficult to make measurement of the slope, which is an important parameter and whose expression has to be used to estimate the 3 unknowns associated with the transfer function model. Thank you.